So let's take a look at the derivatives of the natural exponential function. The derivative of e to the x is in fact e to the x. That's kind of cool. The derivative of e to the x is itself. Let's take a look at a quick proof here. D dx of ln of e to the x is equal to d dx of ln e to the x is x ln e, but ln e is 1, so this is really the same as d dx of x, which is equal to 1. Okay, so I know that d dx of ln e to the x is actually equal to 1. Now, this also implies, based on the derivatives of logs, that d dx of ln of e to the x is equal to, forget about all this, I want to take the derivative of ln of e to the x like I would take the derivative of ln of g of x, because e to the x is g of x. That is equal to 1 over e to the x times e to the x prime, which is obviously just the derivative of e to the x over e to the x. But I know, because I just showed, that this derivative is also equal to 1. That's what I showed right there. So that implies that e to the x prime, which is just simply another way of writing d dx of e to the x, is equal to e to the x times 1, which is e to the x. Now, if I have e to the u, where u is some differentiable function of x, then the derivative is slightly different because I need to apply the chain rule. So d dx of e to the u, where u is some function of x, u is a differentiable function of x, is going to be e to the u, because we know that's true from up here, right? But applying the chain rule, it's going to be e to the u times u prime. Well, really, we did the same thing up here, because this is a derivative of e to the x is e to the x times x prime, but x prime is 1, so it's just e to the x. So if I think of this as a function of x, I could write this perhaps to be a little bit more clear this way. d dx of e to some differentiable function of x, g to the x, is going to be equal to e times, or e raised to the g of x times g of x prime, which we typically write as g prime of x times e to the g of x.